Again, we consider the situation where where light comes in phase from two slits. The slits are separated by distance d, and the wave travels a distance r, some long distance, and finally converges at a point. The two rays that started over here go through some long distance and converge at a point. There is a lag between the two waves arriving of d sine theta. It's a d sine theta lag here. Okay, the wave that traveled further, which will be this one, will be behind the other by d sine theta. And as we've seen, if d sine theta is a whole number of wavelengths, peak will still meet peak. If d sine theta is a whole number plus half of a wavelength, then we'll have destructive interference. Now looking at the whole picture, this distance is r. Let's say this distance is ym, for y distance for some maximum. Okay, so actually it's y distance for maximum number m. M stands for the number of the maximum. We have an angle theta. That's the angle at which these rays come off. They come off practically parallel. This is a large distance compared to this. In that case, in the first place, we see that ym, this distance, is approximately equal to r times the sine of theta. Now r, ym is really the hypotenuse times the sine of theta, but if this angle is small, then the hypotenuse is not going to differ appreciably in length from this adjacent side, and we're safe in saying that ym is approximately r sine theta. That's a small theta approximation. In that case, the sine of theta is going to be, well, not in that case, but the sine of theta is just m lambda over r, because what's m lambda? It's just the d sine theta. In other words, d sine theta is our path difference here. That's m times the wavelength, because we're looking at the fringe number m. Okay, so just rearranging d sine theta equals m lambda, we get the sine theta is m lambda over d, which means that ym is approximately r over d times m lambda, just substituting m lambda over d for sine theta and rearranging. And this equation tells us if we can count out the number of fringes and the distance and compare that with the distance r, it gives us an equation relating that distance ym to r and lambda, which would allow us, if we knew the number of fringes here, to determine what lambda was. So that's a way we could measure the wavelength. If we look at the waves that end up converging at a point here, you remember that this wave is lagging this wave by whatever the path difference is, by d sine theta. Now that might amount to this one being at a phase of pi over 2 and this is at a phase of 0. Remember, the phase is just the argument of the cosine function, or the sine function that's modeling the wave. Okay, so this one is at a different part of its wave than this one. In this case, we would say that phi, we call phi the phase leg, we say that phi is approximately pi over 2. Okay, now that's just an example of what we mean by phase. The phase difference between the two waves, well, what is it? This wave lags this one by d sine theta. So that's d sine theta over lambda of a complete cycle. Now, we've got the ratio d sine theta to lambda of the phase leg over the wavelength, so we have the number of wavelengths phase difference. We multiply that by the 2 pi radians that corresponds to a complete cycle, and we get the phase difference angle. So the phase difference angle is d sine theta over lambda multiplied by 2 pi. In this case, the electric field of one wave might be e cosine omega t. Let's say this one's e cosine omega t. Then this one's going to be e cosine of omega t plus phi, the phase difference. The brightness that we get at this point will therefore be E1 plus E2. We simply add or the electric field that we get, which will determine the brightness. Okay, the electric field that we get, we add the two electric fields here, and we get E1 plus E2. Now, I'm not going to go through the details. We go through a little bit of symbolic trigonometry. We can use the angle formulas for the cosine of A plus B or the sine of A plus B, or we can use what's called phasors, and we'll see those at another point in the course. In any case, we can see that E1 plus E2 has got to be 2E times the absolute value of the cosine of phi over 2, then times the cosine of omega t. So that's the sum of the two electric fields. And again, we don't have to use phasors. We can just use basic trigonometry. You can fill in the dots. It's just a pre-calculus problem to do that. Using that relationship, we see that the electric field E1 plus E2 is 2E times the cosine of pi times d sine theta over lambda. We're just substituting d sine theta over lambda times 2 pi for phi. We divide by 2, we just get a pi. So that's how we get this relationship. Now, since the sine of theta is approximately equal to y over r for small angles, as we saw before, we just substitute y over r for sine theta, and we get this expression. So that we see that the sum of the electric fields is just 2 times the electric field of one of the waves, because remember the waves are E1 equals E cosine omega t, E2 is E cosine omega t plus phi. They have the same amplitude E. So we just take 2E times the cosine of this expression, and we get the magnitude of the electric field, or the amplitude of the electric field at the point Y. We can read this as pi d over lambda r times Y. The variable here is Y. And of course the cosine, as y changes, will change from -1 to 0 to 1 to -1 to 0 to 1, and so forth. So E1 plus E2 will go from -2e to 0 to 2e to 0 to -2e to 0, and so forth. Where it's at -2e or +2e, we have a bright spot. Remember, that happens as y changes. Y is our distance here from central maximum out to here. It's this distance. As we move from here to here, the E1 plus E2 goes positive maximum 0, negative maximum 0, and so forth, according to this equation. The distance delta y between maxima is going to be what? Well, to change this by 2 pi is going to take us from maximum to maximum. This is going to change by 2 pi if y changes by 2 pi over pi d over lambda r, or lambda r over d. Again, just using some basic concepts of trigonometry.